Welcome and hello everyone. So it is my great pleasure to introduce our speaker today, Dr. Mokhtar Alaya. Dr. Alaya is an associate professor of statistics and machine learning at University Technology de Compagne, where he has been teaching in the computer science department and conducting research within the laboratory of applied mathematics since 2020. He obtained his PhD in statistics machine learning from Sorbonne University in 2016. His academic background also includes two master's degrees from Sorbonne University, one in statistics and another in probability and random modeling. In addition, he holds a magister in mathematics from University of Gabes. Dr. Zahdi Alaya is a research interest in statistical machine learning with a particular focus in optimal transport theory and its application, space inference matrix, computing, server analysis, and high-dimensional statistics. So today, he will present the talk entitled Optimal Transport Meet Frequency Gaussian-Smoothed Divergence for Provide Distribution Learning and Domain Adaptation. So, Dr. Zahdi, we can start now.
Thank you very much. I will start by thanking Rafik for this invitation to Al-Khwarizmi Applied Mathematics webinar, and I thank also Mohammed for this presentation. So my talk today is about optimal transport that meet privacy. Actually, optimal transport, maybe for someone who knows, it's linked to probability measures theory. Maybe you know Cedric Villani, who has the mid-ice fields in 2010, why he takes these middle fields, because he's advances about optimal transport theory. But actually, this optimal transport we can use it for doing machine learning pipelines. Why privacy? Privacy, especially nowadays, we have a lot of data, but this data can be sensitive. For example, if you have medical data for some patient and you don't like as a user don't like to hide or would not like to show this the information about these patients. Or maybe if you work with state, maybe there is, for example, here in Europe, we have RGBD regularization, or maybe I think HIPAA in US. So we cannot show any information about this data. So what we can do like blur this data using some nodes. It means that we will hide this data and we will blur it using some Gaussian nodes. Also, I will speak about domain adaptation, which is a very important task in machine learning pipelines. So I will start my talk with. Let me check, with the motivation, that I will start my talk with the motivation, and this motivation, especially one we can use, especially for if you have, for example, for some cloud of points, and the task here is to compare these two data. Okay, to maybe in classical machine learning, you have to separate these two data. You have to classify from the blue data and the red data, or maybe you would like to compare these two clouds of points. For example, it's very maybe we can compare as naively and vanilla comparison. You can calculate the mean of your data, the blue data, and the mean of your of the red data. Maybe if the means are close, you can say roughly that these two data are close. But we would like also to automate this process. Imagine that you have many clouds of points from blue and other points of other clouds of points or red, and you would like to automate to do it by learning using a machine. Another process, another application we can find it in image processing, that you would like to compare two images. Okay, you have on the left one image and the right and one image. So maybe if you would like to compare, maybe I can use the L2 norm of the pixel. I will, because each pixel here is a vector in R3, which is the intensity of green, of red, and of blue. So I can do like L2 norms between these pixels. But why not if I use the distribution of the colors in these two images? For example, here is the distribution of red and green and blue in 3 dimensions. As I said to you, that each pixel is corresponding to vectors and in 3 dimensions. So for the second one also, I can plot or can calculate the distribution of this palette of colors, and now I can compare, instead of comparing pixel by pixel, I can compare it in sense of distribution. So here is very simple, that just two images. But imagine, for example, in CFAR data, 1000K, there is a lot of data, maybe 1 million images. So doing it with this one, it's very hard. So we'd like also to learn this process, this image processing using machines. So it means that using computers. Another motivation example is neuroscience. Is imagine that you work with some, let's say, with doctors, and they have this MRI images for some patients. Maybe a state A, this, for example, before this is the MRI of the MRI image before. Let's imagine that before taking some drugs or some treatment, and the state B is the after taking these drugs, and would like to know which activation maps that was activated. And for this we can work let's say pixel scale, but also we can work also in distributional scale. For classification checks per data, here we have this data that is available and open source data. We can use it for doing classification. We have this checks per data. It means that we have some kinds of some class of pathology, and we'd like the task here is to learn if to build a method or a predictive modeling that learn which kind of or class of this pathology of a new patient. Also, always we can vectorize these images. Just I take one image, I will vectorize it because it's just in blue and no, sorry, in black and white, and can vectorize it. And and doing my classical machine learning using this vectorization, or I can do it using the distributional case. Another for anomaly detection, which is very an important task, especially with medical, is for Bratz data. Bratz data is some MRI for some patient, and the task here is to classify if the patient he has some pathologic with the cerebral cerebral pathology, and Here we can also use a classical machine learning. It means that each images I will vectorize it in some vectors, and this vectors is corresponding to one sample. Or we can do also using this distributional case. It means I will plot, or I will transform my images to some distribution, and I will work with distribution with these samples with these images like a distribution. Another case which is very, very important in genomics, here we'd like to understand the dynamics of an individual cell level. It means that imagine that you have sequencing of some, you have genomic sequence of some patients or some cells from some patients, and you would like to know which in also with imagine that these patients he takes some drugs at in the time t, and we'd like to see, for example, t+1, maybe I don't know, maybe 6 hours, maybe 12 hours. We'd like to know if the red cells, which the origin of the red cells from the blue one. Then this one we can use this transcriptome. It means that we will transcript these cells in using this transcriptome, and the same for the blue, and we get some x and y, which is belongs to RD. D is roughly 20K. 20K, because this roughly is 20K for a genomic sequence. And here the task, as I said, is to know how these dynamics of the cells using from between two times, or according to, or with respect to some scale, time scale, and would like to know if these the red cells are the new cells, and which the origin from the red cells from the blue cells. So the whole how to do this one in using some machine, we have to use what we call it machine learning or predictive modeling. It means that I will build some models that using some the available data. It can be the images, can be this genomic sequence. It can be some I don't know, maybe some distribution. And I would like that if I get new data or a new observation, I just like to infer my models to this new data, and after that I will see my prediction. So for this one, as we said, we have to use this predictive modeling via machine learning. The context, or the whole let's say the whole picture of the machine learning, it's based on what we call training set. The training set, the X is corresponding to the feature space. The feature space, it can be or it can be the available images. It can be I don't know, some client. If you work with some banks, it can be a time series. Okay, this feature space. It means that the data that you use to build your model. Label space is Y. Maybe the patient is this way. It can be this class, like in Shakespeare, in Shakespeare's data, or maybe it's the category of or the type of the pathology that has the patient. It may be we can, if we have this access to this Y, we call that we are in a setting with the supervised learning. If we don't have this Y, it means that we are in a non-supervised learning. It means that we give you some bunch of data, and we would like to structure this data maybe in segmentation clients. I don't know, maybe if you have a big brand of I don't know, of some, or maybe Carrefour or something like that, and they would like to build their marketing company, their marketing. It means that they will cluster, or they will partitionate their clients. I don't know, maybe there are someone they like some products, or or other type of products, and this if this new structure of your data. So we have this xi and yi belongs to x across y, and xi is corresponding to this vector. Maybe xi, it means that this genomics of the sequence genomic of patient, it can be can be vectorized images. It can be a profile of some client. Okay, it can be a patient, his historical, his age, his weights, his all his medical historical medical, and we have what we call is sampling data. It means that the amount of data that you have that you have access to data. Maybe, I don't know, maybe you have n 1000 data, and we'd like to, for example, to cluster or to cluster some client, or you have to classify some patients. They are, I don't know, they have some patient with some pathology, or any kind of prediction. And this is the training set. Okay, and what's the learning task? The learning task consists of assuming that we have some relation between the feature space and the label space. Okay, if this H star corresponding to some relation between x and y. For example, x, if I have my x with the vector of some patient, so it's a class, for example, class of the category of his pathology, or maybe y it can be continuous. For example, the electricity consumption, the electricity consuming, and so on and so forth. Or maybe H star just means that if I don't have access to Y, it means that I will cluster my access to some groups or to some clusters to get a new structure of my data. Okay, this hypothesis, or we call this hypothesis, we call it predictor model, or classifier, or it can be a regression function for statistic, but I prefer to tell this H star as predicted model. So what we'd like to construct our learning model, it means that we will construct some hot H, which is corresponding to H of some theta, hot theta. Why hot theta? Because here we are most of classical machine learning, they are parametric. It means, I don't know, maybe you can approximate or you can learn your regression model or regression function using some polynomial. Your theta, it means it can be some polynomial with some degree, or it can be some inner product between x and some theta. So this h theta, so it's from x and y, and it will approximate your h star. So how can I learn this h star? I need what we call loss function, and this loss function is like a cost. It will be from y cross y to some r plus. And what's the role? The role of this function is to quantify your prediction. I don't know. It means that it will give you some quantity, some value, that if your h of x is close to your predictions.
Can I
H
ask
of
a
x.
question, Mokhtar?
Okay, go on. Yeah.
In your previous example about the example from medicine about the red and the blue cells, what
Yeah.
represents X and what represents Y? Y is the blue cells and X is the red cells, or not?
Yeah, it can be like that. It can be y, for example, here y it can be my y, it can be the red cells. It means that, and x is it's the blue cells, but the blue cells which is in genomic sequence. It means my vector x that belongs to RD.
Okay.
Because I will see maybe the distribution be here I am talking about some in vector scale, but for the cells it means that I will get this distribution of my red and which are the new one, and I would like to know each cells comes from which blue cells. It means
Okay.
that this red cells comes from which the origin for these red cells.
Okay. Mhm.
Okay, so here the red cells it will be some distribution, okay, and the blue cells it will be some distribution because I will transcript them in RD, and each cells it will correspond to some let's say to some sample point from my distribution. Okay,
Mhm.
and in this case this L it will quantify is does this my red cells are close to my blue cells or not.
Okay.
But imagine that it will be when I plotted it or when for my illustration it's just four or for two or for bunch of cells. But imagine that you have many cells and you would like to compare or to see which the origin of these dynamics.
Okay. Okay.
And yeah, just go on.
Okay. More L is close to zero, more we have a good prediction.
Yeah, exactly. It depends. It depends on your task. For example, here, if imagine that and it can be what we call it the hinge loss. The hinge loss is an indicator between y and h of x. If the indicator if equal one, because it's an indicator function,
Okay. Okay. Okay.
it means you made the mistakes and then you pay one.
Mhm.
It depends on the context. It
Okay.
can be, for example, for regression function, it can be the L2 norm, y minus h of x, the L2 norm.
Okay. Okay.
Maybe if I am working with images and with the classification, it can be cross entropy or cross entropy loss function. So it
Okay.
depends. The choice of this loss function depends on your learning task. I cannot do any I cannot, for example, do L2 norm for some classification.
Mhm.
It can be, but it's
Suitable.
not meaningful for my class or
Okay.
for my task. So this is very important. Actually, this is very important for this choice for this loss function to for your learning task. And now, what are the theoretical question that we ask about this learning task? We'd like that our y or our h hat it will be more closer to my prediction. But before that, we will define what we call real risk. It means that there is some real risk of your predictor. If you I don't know if you for example if you have let's say if you have regression function which is polynomial regression function which is polynomial and you would like to approximate it or to learn it using a single let's say a single line. You see this huge bias between your polynomial regression, let's say is of degree 2 or 3, and you'd like to approximate it or to learn it using a single line which is in the form of a theta plus b. So this is what we call that you will pay some you will get some risk, which is the expectation of with respect to your probability, because when you because your xi and yi they are only some observation from your probability p, but unfortunately this p is unknown. For my case, for my learning, this p is unknown. So my real risk r of h is the expectation and my cumulative error with for my predictor h. And what we'd like to minimize this risk, but this risk depends on the probability p. But I don't know, for example, how my because the probability P is joint law, the joint probability for my Y and for my X. I don't know what is this joint probability. It's unknown. I don't know how, for example, if a cancer, cancer pathology, the joint probability between for cancer pathology and some patient. This one is unknown. I don't know how it's distributed. But the idea, what is the idea? Because I have access to my data, I will replace this joint probability, which is unknown, with its empirical probability measured Pn. And Pn, it's 1 over n is the Dirac atoms in XY and yi. This is the definition of empirical probability measures. So if I have this empirical measure, I can define what we call it the empirical risk minimization. Empirical risk minimization Rn of h, which is the average of my error or my loss between ya and h of xi. And this one is I can calculate it because I have access to ya. Of course, if I am in supervising learning, I have access to h of xa, and I can calculate this one because I have the data. I can calculate it. Just I have to check, not to check, but to take to get some loss, and I can calculate it. And this error of h, if I have using the central limit theory, this error of h converges to the real risk, because hl of ye and h of xe, they are EAD, and so using central limit theory, this error of h converges to n of h. But from practical point of view, this h of theta star, it means that I will search my h or my theta corresponding to some, what we call it, to some hypothesis class. But why this hypothesis class? Because it's impractical, it's intractable to learn all the function or all the relation from x and y, corresponding starting from x and y. This is impractical, intractable and impractical in the same time, because what we see here, okay, they said we will choose some class, capital H, and we learn inside this class. Of course, we will get some biases. These biases with this approximation, because imagine this whole x, all. Let's take example, for example. Imagine that, I don't know, you have some regression function and you say, okay, that's from R to R. So in implementation, I cannot draw all the functions that start from R to R, but we can say, okay, I will work only with polynomial function, and this H corresponds to polynomial function. Because of course I have some biases with the approximation between all the functions start to R from R with the polynomial function. I don't know. There's in chat. There is some question now. Rafiq, please, if there is any question, because I cannot see the chat. If there is any question,
Okay.
you can tell me, please.
Okay, sure.
Yeah. So some part of my research, I am doing what we call it some oracle inequality. Oracle inequality, it means that if there is some theoretical guarantee between h stars, h hat theta and h stars. Of course, we can add some other, let's say, some other control about some h. We can add some, let's say, some penalty or some penalty to my h. Imagine, for example, in the case that you in high dimension statistic, for example, especially in genomics, let's say if we have all the sequence of genomics that's d in RD, and d is roughly 20K, and you have only let's say 20 patients, and you would like to learn some some prediction models that you said, okay, this patient it has some, it has, it's this, let's say this cancer pathology, it can be explained by the gene 1, G2, till gene number 20K. This is not possible because you have a high dimensional setting. What we can do, we can add some penalty of norm L1, it can be norm L2 to my Rn of H. And this one, we call it the empirical risk, the penalized empirical risk minimization. Okay, now my, let me return, as I said, this L, it can be a loss function, this loss function. It can be L2 norm, it can be cross entropy, it can be hinge loss, it can be any loss that that is suggested, for example, by the expert or by you as a project, by you as a user for this data. But also imagine now if we are working with not with vectors, but we are working with distribution. And that's why we need this distance between distributions, and that's why the role of this of optimal transport in this case. Check it's working. Yeah. And the role is optimal transport that brings this notion of comparing between two distributions. The origin of the optimal transport is to Gaspard Monge, which is French mathematics, to 1781. And in Gaspard Monge, the problem here is to compare to because there is he needs this notion of optimal transport to let's say to take some sand from some point and to send it to another point. This, let's say, for our notation, this sand, it will be the Debye, okay, and it will be tracked and it will be filled to other distribution, or to other simple to other tranches of sand, which is the Rombley. And the question here is how to move dirt from one place, or this sand from one place to another place, but with minimizing the effort. It means that for Monge, he reformulated this question or these needs as finding a map T between these two distributions. And this map T, it will be transport the mass, a bunch of mass or a portion of mass from mu to nu. Of course, we'd like to optimize with respect to some displacement costs. For example, here, if I have a portion of mass of x, I will transport it to nu, sorry. And this transportation, I will apply this mapping and this t of x. Of course, I will pay this cost. It can be, well, let's say, for example, this cost, it can be L2 norm between c, some cost c between x and t of x. And in the it's not like our days. In the day of Monge, they don't have a mechanical engines to get this one. They do it by hand, and they will transport this portion of mass from x from mu to nu. And here, this t, it will push forward the distribution mi to nu. Like this, we call it t ds mu what's equal to nu. It means that with the probability, it means that nu of applied to some Brown of some Borelian, nu applied to some Borelian b, it means that it will be mu t minus 1 of b is the pre-image or the pre-image of this Borelian. And the Monge formulation, it will be like that. It aim at finding the mapping T such that it will minimize the cost between x and t of x. Of course, when I transport a portion mass from X, I will pay this mu of X. But this mapping does it not exist in general case. Why? For example, if you take, let's say, 1 Dirac in 0, this is your mu, and 2 Dirac for nu. That's Dirac in -1 and Dirac in -1. This is not possible because this mapping doesn't exist. It cannot, for example, you cannot say t of 0 equal -1 and t of 0 equal 1. It's not possible. Rather, for example, if my C is the L2 norm, Brunier in 1991, he proved the existence and unicity of Monge map, which is a jewel crown of when the cost is L2 norm. And he proved that the existence that this Monge map, this T, this mapping T, existent and is unique. This in let's say in continuous setting or framework. If we do it in discrete OT, because in machine learning we don't have access to this continuous framework. We have access to some samples, and for example, I don't know if you have these images of this sequence of genomics. You can do like uniform distribution. Each images you can put you can do it. You can consider it like a Dirac, and you put 1/n. It's mass. So this C A of G, so it will be this cost between xi and yj. Mu, it will be a discrete distribution. Okay, imagine that mu I, it can be 1/n. Okay, it's 1/n. And what we'd like to minimize this, I don't know, where is my cursor? Yes, yeah. We'd like to minimize this cost between xi and t of xi, and I will pay. Of course, I will transport this mu I, which is my mass. So t push forward for mu equal nu. I can write it in this discrete optimal transport that for any j, nu of j, the mass of nu of j is equal to the sum over mu I, of course, applied to t of xi equal yj. This is discrete framework for the Monge problem. But for the Monge problem, this, what we call it, is a deterministic assignment, because Monge would like to get some bijective mapping. It means that each xi should be mapped to one yj, of course, with respect to this push forward. But as we said, this problem suffers from many difficulties and many backbone. For the first one is combinatorial, because if you consider, let's say, uniform weights, that 1/n everywhere, and you will minimize over all the permutation between xi and y sigma I. It will be a combinatorial problem. It's non-existent, as I said, non-existent. For example, here, if you have 2 Diracs, and you would like to transport the uniform to these 2 Diracs, is not possible. And also is non-convex. If you have you have, I don't know, lambda t1 plus 1 more lambda t1, I can give you some example, but it's not convex. So this problem is still open till, I think, 160 years. It's still open till the approach of Kantorovich. Kantorovich, they said, the whole picture of Leonid Kantorovich, they said, okay, I will relax these assignments. I will fraction the proportion. It means that for mu I, if I have some mass from xi, I can fragment it to some two points or two or 3 points that from distribution of nu. And it means that I have some. I will this relaxation of this assignment. It means that give me that some mass conservation constraints, which is defined by this polytope py p nu of nu. It corresponded to all these matrix which are positive or stochastic matrix, and they have this mass conservation constraint. So for his formulation, Leonid Kantorovich, he gets the Nobel Prize, I think, for economics for economics for his formulation. And the Kantorovich, it means that the computing between optimal transport between mu and u it will be a linear problem. It means I will search from all the stochastic matrix P and this inner product or this trace between my cost C and P. We call it this Monge-Kantorovich, or also later we will define it as the Wasserstein distance. This is in discrete OT framework, in which is what is this corresponding to the continuous OT framework. My P continuous between mu and nu, it will be a joint or the probabilistic coupling. It means that it will be some joint probability between mu and nu. If I project with respect to my RD, I will get with respect to my RD, for example, gamma. If I project with respect to y, I will get nu. If I project with the direction, but with respect to x, I will get nu. This is the transport polytope in continuous way. And here's this joint distribution in my illustration. This is nu, and this is mu, and this is joint distribution. Of course, this P continuous is not empty, because I can the product measures between mu and nu belongs to this P continuous. So now, here the choice of this C of xy, because we'd like that this transport, this optimal transport, should becomes some distance. If I choose x, my cost, like for example, some dp, some d, and d here is a real distance or proper distance, so I get my Wasserstein distance. Or Wasserstein distance is very, let's say, is very, okay. For my Wasserstein distance, I can choose this d like the L2 norm to make it simple as possible. The L2 norm or the L2 norm power to p, and we can get this Wasserstein distance. Of course, this is the formulation. I can also is the infimum over all, because I forgot to say this. The infimum of to put it is the infimum over all the joint probability gamma, and I would like to minimize this expectation with respect to x and y. It means they this is, let's say, the probabilistic formulation of the Wasserstein distance. I can see it like Wasserstein distance. For literature, there is the chapter 6 of these books of Cédric Villani. There is a lot of theoretical results about these Wassersteins. It's a real proper distance once your this d is a distance, because it means that we know that WP of nu equals 0 if and only if mu equal nu, almost sure, and triangle inequality, and all the property of the distance. The third book is about computational optical transport, written by Gabriel Perry and Marco Ciccioli. It's about the implementation of optical transport in discrete and continuous way. Some example here, W1 if mu between mu and u is, we have a closed form, which is roughly is the average of the area between the CDF of mu and the CDF of nu, is the difference between these two CDF, and we calculate this average. It means that if the two CDFs are closed, so my distribution are closed. For if I have, let's say, if I have some Gaussian distribution in R2, so I have what we call it the pure distance. It means that the difference between the mean plus a term that is with respect to the covariance matrix. So what are the benefits of these Wasserstein systems? Because we'd like to use this Wasserstein distance, especially in learning and in training deep learning model. The model here my illustration, it's just only I translate some distribution. Okay, the blue is the same. Just we translate the mean of this distribution, and we can see that the L2 is very sensitive to this local point, because here my illustration, they are the same distribution. Just I shift the mean, and we see that the Wasserstein distance, it reflects the geometry of your distribution. Comparing to this L2, which is explode, it means that this explode is don't let's say don't reflects my distribution. Here they are the same variance. Just I shift the mean. I shift the mean of my distribution. We see that the L2 explodes. The L2 norm explodes. The L2 one is roughly acceptable, but we see here that for the Wasserstein distance, that is linear. Just because I am roughly it reflects the geometry of my distance. Another kind of another illustration is between W1 and the L2 and the total variation. We can see that here I said that my source, this is in yellow my source, and in purple is my target, and just I translate this distribution, this density function. Okay, and we see here that the W2 is reflect that are very that the W2 is higher than the L1 and the L2 and the TV, and this one is very important when you learn, for example, when you learn deep learning network. Why? Because if you use, for example, the L2 or the L1 or the total variation of the Kullback-Leibler divergence, if your gradient, let's say if your if the gradient, if I have calculate some gradient with respect to my W, so my Wasserstein distance, it will be significant, and after that I can learn I can push my learning, my task learning about my let's say about my deep neural network. Another here is with comparing with the Kullback-Leibler, the Kullback-Leibler divergence. He has a problem, which is if your distribution are not overlapping. If your distribution are not overlapping, so the Kullback-Leibler, it will be infinity. And if you use this one, as I said, in machine learning or deep learning training, you have the Kullback-Leibler is infinity, so you cannot do anything about your gradient and so on and so forth. Here in the bottom, I clapped my the KL at 15, because the KL, if your distribution if you don't an overlapping support of your distribution, the KL, it will be infinity. So for purpose of the purpose for my illustration, I clapped it in 15 to get this this illustration. And we see here that the Wassersteins, it's stable and it reflects that the geometry between my two distributions. Okay, so how can be used this optimal transport distance, this Wasserstein's distance in data science? Here I took this picture from the HDR of Remy Flammary, and we see starting from 2013, it will be using of this optimal transport is in numerical application in machine learning and deep learning, and especially it puts this the generative adversarial network in deep learning. It means that it's the paper of Goodfellow in 2000, I think 2014, which is about Wasserstein's generative adversarial networks. It can be used. It replaced the Janssen distance using in the GAN. It was replaced by Wasserstein distance, and the deep neural network, it was more stable in this case. It can be also for matching words embedding. It means that imagine that you have some books, some documents, document one, like some books, and another document, another books, and you'd like to see or to learn if your or these two books are they have the same they are close in distribution setting. So what we can do, it means that I can embed my docs or my books in high dimensional space with the deep neural network, like Word2Vect or Glove. Okay, we can embed this one, and after that I can matching these two documents in OT in optimal transport way using this distribution. For example, here Obama speaks to the media in Illinois. It can be the same things like the president greets the press in Chicago. It's just a toy example to see to how to use this matching words embedding using an optimal transport of Wasserstein's distance. Another thing that is the GAN. The GAN, it means that you have the GAN. It's this deep neural network that has a generator and a discriminator. And here, for example, my real data is these two blues, these two modes, the first mode and the second modes, and I will start from nodes, okay, and I will generate nodes. Till I get my real data. This one especially for generative for GANs, and as explained before that these GANs I can use can use the Wasserstein distance between my data that are starting from nodes and my real picture. It means that, as you can say, let's say you have some celebrity images. Okay, I don't know, you have many celebrity images. You can start from nodes. Okay, you generate nodes using first architecture or first deep neural network, artificial and deep neural network. Okay, and you have some discriminator, and this discriminator he will try to adversarial if your generative is a fake or is real data. And the paper of Arjovsky and all, they said, okay, they use the Wasserstein distance, and they create more stable. And of course, this here in my example, this ZA is some random vector, and XJ it can be some images. Here for generative, let's say it's a basic of for generative modeling or generative artificial intelligence. Yeah, generative model.
Mokhtar.
Yes. Yes.
Please, you have 2 minutes just to.
Oh my God.
Sorry.
Okay. So another case of domain adaptation. I will be like domain adaptation in classical learning. We have test data and train data. Train data, we suppose that the train and the test comes from the same distribution. What happens if if the train data and the test data they have different distribution? This is the core of the domain adaptation. Domain adaptation, it means that I will train my model using machine learning on my source domain and my target domain. I would like to transport this my source. Okay, I will try to transport this source data and this domain data that comes from different distribution. I will transport it my source data to the domain data, okay, to the target data, and after that I can do my classification transport. Of course, here there is three-step strategy. We suppose that we have some transport from my source to target. Then I can try or learn my classification using this transported data. This is the whole or the big picture of domain adaptation. Domain adaptation return that your train and your test, they don't have the same distribution, and you would like what we can see. Of course, let me give you an example. If you have some images, a cat or a dog or horse, they are the same images, but you change the domain. For example, you put more brightness, or you change the angle of taking the picture. It's the same picture, it's the same label, but the distribution is different. And this one, for if you do some machine learning pipelines on this distribution, on this data, you will get a worse performance. That's why we'd like to use this optimal transport to transport my source data to the target data, and so on. In my transported samples, I can do my classification like SVM, like regression, and so on and so forth. I would like to go to the smoothed and sliced. It means that there is a statistical problem using the Washer science. This is what is the curse of dimensionality. If, for example, of course, if I don't have access to my real distribution, what I said, I will approximate this empirical distribution, and the curse dimensionality between for my Washer synthesis, it is that the expectation, the Washer distance between this empirical, because it can be implemented, and the real one is roughly n over n power to 1 minus 1 over d. It's very the rate of convergence is very slow. And also another thing is that the linear programming that required to calculate this Washer statistics, it's linear programs. It's let's say its computation is of n cube, and this one also another backbone of my using this Washer statistics. But for d equal 1, if my mu and my source and target distribution are in RD in R, a real distribution, I have a closed formula for this Wassersteins, and for the empirical, it's only I will sort my data. Okay, I will sort my data for X. I will sort my data for Y. Okay, and after that I will average this sorting. And the average of these sorts, it costs me only O of n log of n. It's very fast. We'd like to use this Washer distance in one dimension. We'd like to use this capability of optimal transport of Washer distance in one dimension. How to use it is this is the Washer distance for one dimension, because, as I said, is quantile matching. We'd like only to project to some random one dimensional space. It's like that. If you have your distribution mu and your distribution nu, just you get your one direction in the sphere, and you project your mu and nu. And in this projection, you will get a new distribution R mu of mu, and this R nu of mu is the push forward of the distribution mu with respect to the linear projection, which is x transpose mu with respect to this direction. And these are 1D projection, 1D distribution, and so on. And after that, I can calculate the Washer distance between this projected distribution. And we call this one the sliced Washer distance, because I will choose many directions in the sphere, project all of them, and calculate this distribution. Here, the complexity of SFW is O of LDN, LDN corresponding to your projection, and LN log of N is corresponding to sorting your sample. L is corresponding to the number of projection of mu. It means by maybe L you can get one direction in the sphere, and you project all your distribution in this one direction, and you get this complexity. Another another approach to tackle this curse of diminution, we can use what we call it the smoothed Wasserstein distance. The smoothed Wasserstein distance, it means that is really important when you have some sensitive data. Imagine that you work with some medical data and you would like to for some patient, and you would like that the users of this data doesn't have any idea or any information about this user. What we can do, we'll blur this data with some noise. It means I will convolve my new and mu with this Gaussian smoothing, and I will get this WP with respect between mu with this convolution between mu and sigma. There is some statistical. This one it not suffers from the smooth Wasserstein distance. It not suffers from the curse of diminution because the WP between the empirical version and the true one is n over minus one divided minus n over minus half. Okay. So for our case, we generalize this the smoothed Wasserstein distance, what we call to tackle or to get into account other divergence. Is not only the Wasserstein distance but other divergences. One of the divergence is we propose this sigma Gaussian smoothed piecewise divergence between two probability. It means that here I will put maybe it can be Wasserstein distance. It can be a Sinkhorn divergence. It can be MMD discrepancy. It can be any kind of divergence. For example, if it is Sinkhorn divergence, there is the paper of Marco Couture that he proposed the Sinkhorn divergence. And Sinkhorn divergence, it means that I have this formulation. For the idea of Marco, it added this entropy term because it's added to entropy term to make the problem of, because it's linear programming is not stable, that if I added this entropy term, I make my problem is strictly convex, so I get one solution. But here, and I gain in complexity, it will be O over, roughly it's O over n square. There is also the maximum mean discrepancy. The maximum mean discrepancy, just you have to define some RKH space and you define this kernel mean embedding. Here it's not they didn't take of the geometry, but it's based on kernel mean embedding, and it has this let's say this formulation. For us, what we get, we have some topological property about this Gaussian smooth divergence. We have that proper of metric. This is proper metric. It can metricize the weak topologies. It's a lower semi-continuous. That is topological property. We have also some statistical property. Statistical property. Why? Because for our case, we have to sample from mu, okay, to get this empirical version of mu, and after that we have to sample again from this convolution, because we have some lemma that this convolution between if this push forward of my let's say this push forward for my empirical version, if I convolve it with my n sigma, with my Gaussian nodes, it's a mixture of Gaussian, and this one is a continuous. So this is a continuous measure. So I have to sample again from this continuous, and we have what we call it this double double empirical smoothed because I have to sample from my origin distribution. Okay, I will project it with the same direction, but if I project it, I will not get a discrete distribution. I will get a continuous distribution, and I have to sample again from this continuous distribution. That's why we defined what we call double empirical divergence. Another thing we have, okay, we have this statistical property that we have roughly convergence rate with between this double empirical sampling process between this double empirical the double sampling process and the true one, the convergence rate of O of n minus 1 divided by 2p. We do it for domain adaptation. Domain adaptation here we have we have this J is like extraction features. Imagine you have your image. You have to this J's. It will be a deep neural network. Okay, and you have this distance D. It can be discrepancy because you have in domain adaptation. It means that your source data and your train data, they have the same label. Okay, the same class, but they are different. They are different distribution, and you would like to take into account this difference between your source and your target. That's why you have to define this, let's say, this divergence between empirical distribution. And we have some experiment that's, for example, for MNIST and USPS, that there are two data. You see that we have the same class, but the distribution is different. We study according to this level of noise. Okay, we have this our performance in the accuracy that of course here we don't lose the accuracy if we blur our data. Another here, of course, if my sigma, my level noise goes to infinity, so it means that my data I will lose some performance in my accuracy. But this sigma, it will be also how to choose this sigma. It can be a real question. How can we choose the sigma, or which the best level for my noise? Of course, we have some other property, theoretical property with respect to this noise. It means that with respect to this noise, here the data are for computer vision. It's for computer Office 31W, and this from webcam. Here from some image from Amazon, and here's some image from webcam. Okay, they are let's say benchmark that we can do. We can find it in the open source, and we can do this one. Okay, this my take home message for this talk, that this theoretical optimal transport, it means that it links between it uses the geometrical information about your data, and it's a let's say real handmade for manipulating distribution in machine learning, because classical machine learning we use this our sample are like a vector, or we can vectorize our image. But why not if we can use this distribution case of our data? Other OT aspects, there are what you call it Gromov-Wasserstein distance. It's Wasserstein distance between Wasserstein distance like between structured data, because for Wasserstein distance I have that my source data or target data, they belongs to the same space. But imagine that I have source data that, for example, in R2 and target data in R3. So in this case, I will use this Gromov-Wasserstein distance. There is also multi-margin optimal transport, MOT. It means that I have many, because we are in B marginal, because I have source and target. What happens is I have many distribution, okay, K distribution. They are with multi-margin optimal transport. And okay, this privacy is the let's say the privacy side for using the optimal transport is by adding this noise, and this noise it can be benefit for sensitive data or privacy issues for using your data. It means you can use your data, okay, but you can hide this information. But also we can use this Gaussian smoothing to tackle this curse dimensionality of Wasser's distance. There is there is a Python optimal transport that I collaborate with the colleague, and we publish this Python optimal transport library. There is a lot of examples that you can handle them if you like to know more about optimal transport. Thank you very much, and I finish my talk. Sorry for if I make it too long. Sorry.
Thank you, Dr. Mokhtar, for this nice talk. I start by my question. What are the main limitations of the proposed method in high-dimensional real-world data sets?
As I explained that for the Washer distance, that is the curse of dimensionality. It means that here, for example, if for practical way or practical data, we have that an expectation. Actually, the expectation of the Washer distance between the empirical versions of your data and the true one is roughly n of minus 1 over d. Imagine in genomics, it means that d is roughly 20K. It's very, 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 very slow. This is statistical from statistical way. It means that you are very. It means that the w the mu n is very, very, very to converge for the real one in slow way, in slow rate. This is for that's why there is this proposition about this sliced, because the sliced one the sliced one, it's if the expectation or the statistical property of the sliced Washer distance between the empirical version of the distribution and the true one is n minus to 1 half, which is very, very very fast. And another thing, this computational burden is O of n3, because here if you like,
and this computational big O of n to the power 3 multiplied by log n, when d equal 1, it is becomes big O of n log n. What about for d equal 2 or 3, for example? It is the same.
For d equal 2, it will be very fast. It will be n over minus half. But imagine it's not scalable for d equal 20K for genomics. Imagine that you are working with genomics data. It will be very, very slow. Very slow. It means that what is that? Let's say the consequence of this one. It means that you have to need more data to get let's say to start getting between parentheses a fast convergence.
Okay. Cyril, could you ask your question, please? No, Mac. Okay. The question of Cyril Bandelier is on this slide. On this slide. Can you explain more the last point about LP requires arithmetic operation? Is the red complexity and why?
Because you have a linear programming. In the linear programming, if you have mu and nu, they have same dimension, the same samples n of n. This is a very known results from linear programming. It's O of n over n cube, because you can use here the simplex method, the simplex algorithm to calculate, or Hungarian algorithm to calculate this one. Because I don't know how to explain it. But starting from linear programming, it's well known that it's O of n square
Okay.
and n cube. But here, for example, the break is let's say the break contribution of Marco-Couturier. Marco-Couturier, they said, okay, I will add this negative entropy because in of course, if I add this negative entropy, I will have some bias. I will be a little bit some bias between the true optimum transport, and this second divergence. Because in the true one, it means if this regularization parameter is theta if theta equals zero, so I will get my true Vasher size distance, or my true optimal transport. But in my true optimal transport, the one is not stable because I can get more let me explain it. It's more here, for example, the Birkhoff polytope. Okay, this C is my cost. And there is no unique solution because the solution is in the, let's say, in the solution are in this point. The solution, it can be in this not in vertex, but in this point. But the problem here is not stable, because if you change a little bit, if you have some noise of your data, so your C is affected, and after that you can get a new solution. So the idea of Marco is to add this negative entropy, is to push these p stars inside this polytope, and to push it inside this polytope. That's why we get this O of n square.
Okay. Another question from Cyril Bondelier. The red quantity was average case cost. And where is coming the log n to the power 2 from?
Oh, log of n, as I said, is coming from the linear programming. They have to because linear programming for linear programming, this one is the computation of simplex method or Hungarian algorithm.
Okay. And this quantity is the average case cost, the red quantity, the big O of n to the power 3 log n square.
It's the computational cost. It means that you need O of n square, log of n square operation to get one solution, solution for this one. It's the operation of, I don't know, if you have your algorithm, so you need this roughly O of n square of n cube operation to get solution for your problem. It's the computational cost.
Okay. My last question is about the perspective. Can the proposed Gaussian-Smoothed divergence be extended to non-Gaussian smoothing distributions?
Yeah. This one, that's why it can be yes, but it is an important direction for future is to consider non-Gaussian distribution.
Okay, so you have no answer.
Okay. Yeah, no, I don't know. I have no answer for this one.
Finally, if you can go to the slide 14.
14.
Yeah. 4-1. 1-4, sorry. 1-4.
Oh, 14, sorry. Yeah.
What about theta hat here? What is theta hat? What represents theta hat?
Theta hat, as I said, my edge, my hat edge is parametric, you know.
Okay.
It's parametric, depends on this parameter theta.
Okay. Example, is the parameter of the parameter of the distribution?
No. In this case, I am talking about it can be for distribution. It can some parameter of my distribution, like here for my gain. Where is my gain? Yeah, here. There's f theta.
Okay.
F theta is some parameter of my distribution. Yes, it can be my some parameter of my distribution.
Okay, and what represents theta hat? is an estimator of theta or what?
Yes, it's an estimator of theta. Is
Okay.
my let's say my output of my training data of my training algorithm.
Okay. Are there other questions, please?
Yes.
Yes, Dr. Mohammed.
Yes.
Thank you, Dr. Mokhtar, for this nice talk. So my question, what the role the Gaussian perturbation play in stabilization optimal transport distance? The role of the Gaussian perturbation.
So there is for this blurring using the Gaussian, it's so there is two let's say two objectives. The first objective that you would like to blur your data. It means that you let's say you work with the sensitive data with the privacy data. I don't maybe some states don't like to get the whole information of the data. What you mean? It means you get these samples, you get this distribution, and you convolve it with this with noise. You convolve it with noise. If you convolve it with noise, you cannot. You get a new distribution that doesn't reflect that can't reflect but is blurred. For example, if you have one patient, one atoms of a patient, and you added this blurring, so you hide the raw formation. This is for blurring and for privacy objective. The second thing is that if I added this Gaussian, I gain in some I gain in statistical property, because here the Weierstrass distance between the Gaussian the Weierstrass, sorry, the smoothed Weierstrass distance between the empirical one and mu and the true one is n over minus of
Minus
n
half.
power minus half. And here, even if your row distribution belongs to RD, it's independent of D. This is the great benefit of this smoothing version. You can take this two objective.
Okay.
Okay, Ibtisam, you have a question?
Yes, please.
Yes.
Thank you, Mokhtar, for this nice talk. So my question, if we have two measures with this disjoint support, can they converge in Wasserstein distance?
Yes, because Wasserstein distance it meteorizes the weak topology. If you have, let's say, the sequence of distribution mu n that is converged weakly to distribution mu, if you can get this if and only if the Weierstrass distance between mu n and mu goes to 0.
Yes.
But for Weierstrass distance, it means if you pick, for example, the the Dirac in 0 and Dirac in 1, the Weierstrass distance between this one is equal only 1. You have one, let's say, Dirac in 0 and Dirac in 1. If you calculate the Weierstrass, it will get just only 1.
I think here, if you have two Diracs in X and Y, the distance is the distance between X and Y, no?
Exactly. Yes. Exactly. Is the distance between X and Y? Exactly.
Okay, thank you. And do you have any idea about application of optimal transport in stochastic control?
In stochastic
Control.
control. Oh my God.
Yes.
Okay, there is the martingale optimal transport, but actually it's the work of Nizar Tuzi, I think in 2014, but I did I didn't get involved in this direction, but I think it's very important to, because I know that it exists for martingale optimal transport. It means that you have some martingale, I will transport from one to one, but I have to motivate it by this financial purpose of using this one. Roughly, I didn't get involved in this direction, but it's very important, I think. But in control, maybe in control we can, I don't know, maybe this is some intuition, but maybe the control can be presented by some distance, using Vachar science distance between the elements, or between the quantity that you would like to control.
Mhm.
I know, maybe if you have, I don't know, martingale in first scan, I don't know, or in the start point, and martingale after, I don't know, after t times, maybe you can control this the distribution of these two using the Vachar science distance.
Okay, thank you.
Welcome. Thank you.
Thank you for the audience. Thank you, Dr. Mokhtar, for this nice talk, and see you after 1 week with another talk. Thank you.